For billions of years, a colossal black hole has been hiding in plain sight at the center of NGC 3840, the brightest galaxy in the Leo cluster, roughly 300 million light-years from Earth. Weighing about 9.7 billion times the mass of the Sun, it now appears quiet and inactive, a sleeping giant that may be the faded remnant of a once blazing quasar. Today, we explore how astronomers measured this monster and what it reveals about the growth of galaxies and black holes. If you enjoy journeys to the extreme edges of gravity, please like, subscribe and share, and tell us in the comments, what would you ask a black hole this massive lurking in our cosmic neighborhood? Thank you for watching. Now let's begin. On the largest accessible scales, matter in the universe is not distributed randomly, but follows a pattern that astronomers call the cosmic web, a three-dimensional network in which galaxies, galaxy groups and galaxy clusters trace out long filaments and dense intersections separated by wide, relatively underdense regions. This structure arises naturally from the growth of tiny density fluctuations present in the early universe, imprinted in the radiation that becomes the cosmic microwave background and amplified over billions of years by gravity. In the standard cosmological model, most of the matter is dark matter, a form of matter that does not emit or absorb light, but responds to gravity and provides the main scaffolding for structure formation, while ordinary matter, mainly hydrogen and helium gas, falls into the potential wells defined by the dark matter distribution. Numerical simulations of structure formation which evolve a mixture of dark matter and gas forward in time under gravity, and the expansion of space show how an initially almost uniform medium develops into a network of knots, filaments, and sheets. These simulations reproduce the large-scale clustering statistics measured in galaxy redshift surveys, indicating that the cosmic web is a robust outcome of gravitational instability in an expanding universe dominated by dark matter and dark energy. On the intersections of filaments, matter accumulates to form the most massive bound structures, galaxy clusters, which contain hundreds to thousands of galaxies embedded in a common halo of dark matter and filled with hot diffuse gas. Along the filaments, smaller associations such as galaxy groups and individual massive galaxies are connected to these cluster nodes, while the spaces between filaments, often called cosmic voids, contain relatively few galaxies and have lower average matter density. On scales of tens to hundreds of millions of light-years, this pattern of dense nodes, extended bridges and empty regions defines the architecture of the nearby universe as revealed by large spectroscopic surveys that map galaxy positions and redshifts over wide areas of the sky. The characteristic features of the cosmic web can be quantified by measures such as the correlation function of galaxies and the power spectrum of matter fluctuations, which describe how clustering strength varies with scale, and by methods that classify regions into filaments, nodes, sheets and voids based on local density and tidal fields in simulations and observations. The gas associated with the cosmic web exists in multiple phases. Some of it cools and condenses into the interstellar medium of galaxies where it can form stars. A significant fraction remains in more diffuse form in the intergalactic medium, partly photoionized by the ultraviolet background radiation produced by young stars and active galactic nuclei, and partly heated to high temperatures in shocks as gas flows along filaments and into cluster potential wells. This warm to hot component, often called the warm-hot intergalactic medium, is difficult to detect directly because it is tenuous and emits weakly, but it is a natural prediction of structure formation. Models and traces of it are observed through absorption lines in the spectra of distant background sources and through low surface brightness emission in X-rays and the ultraviolet. The cosmic web, therefore, is not only a pattern of galaxies and dark matter, but also a network of gas flows where material streams along filaments, feeds into forming structures, and participates in repeated cycles of cooling star formation, feedback from stars and black holes, and reheating. On the theoretical side, the emergence of the cosmic web can be described in terms of the growth of small perturbations in a nearly homogeneous universe. Early analytic models approximate dark matter as a collisionless fluid and follow the evolution of overdense regions under gravity, showing that structures collapse first along one axis to form sheets, then along a second axis to form filaments, and finally along a third axis to form approximately spherical knots. This picture is borne out and extended by high-resolution cosmological simulations, which reveal the detailed morphology of filaments, the substructure within dark matter halos, and the history of mergers and accretion that build up massive systems. The spatial pattern of the web retains memory of the initial fluctuation field, including characteristic scales set by processes in the early universe, such as the propagation of acoustic waves in the photon baryon fluid, before recombination, which leave weak but measurable imprints, like baryon acoustic oscillations in the galaxy distribution. Observationally, three-dimensional maps of galaxies constructed from wide-field surveys demonstrate that on large scales the distribution of luminous matter follows a filamentary pattern similar to that seen in simulations. Galaxies trace out chains that extend across hundreds of millions of light-years, converging into denser knots where the galaxy number density rises, and the velocity dispersion of member galaxies indicates deep gravitational potential wells. In these regions, hot intracluster gas can be detected through its X-ray emission and through its interaction with the cosmic microwave background radiation via the Sunyaev-Zeldovich effect, providing independent measures of the total mass and thermodynamic state of the cluster environment. In contrast, the void regions show fewer galaxies, lower peculiar velocities, and lower gas densities, contributing little to the overall baryon budget, but playing a role in shaping the dynamics of surrounding structures through their underdensity. Within this framework, galaxy clusters occupy the nodes of the cosmic web, while superclusters can be viewed as large-scale associations of clusters and filaments that share a common dynamical environment on scales of hundreds of millions of light-years. The positions and properties of clusters, their spatial correlations, and their internal masses and gas contents together provide strong tests of cosmological models and of the physics of structure growth. Clusters in the nearby universe thus serve as laboratories for studying galaxies and intracluster gas, and as traces of the underlying web of matter that extends far beyond the confines of any single system. They lie at the crossroads of filaments through which matter continues to flow under gravity, even in the present epoch, reflecting the ongoing slow evolution of large-scale structure in an expanding universe dominated by dark energy. On scales larger than individual galaxy clusters, observations and theoretical models show that these systems themselves are grouped into extended associations known as superclusters, which contain multiple clusters, galaxy groups, and interconnecting filaments within a common large-scale environment. A supercluster is not usually a single, fully gravitationally bound object in the same way as an individual cluster, but rather a region where the density of matter traced by galaxies and dark matter is higher than the cosmic average over distances of tens to hundreds of millions of light-years. Within such a region, several galaxy clusters can lie along the same filament, or at nearby intersections of multiple filaments sharing similar large-scale flows and participating in a common dynamical context. In the nearby universe, examples include the structures historically labelled as the Virgo supercluster, and more recently the larger-scale entity named Laniakea, which encompasses the local group containing the Milky Way, the Virgo cluster, and a broader network of clusters and groups. In these cases, three-dimensional maps built from galaxy redshift surveys reveal that clusters, groups and field galaxies occupy a region where peculiar velocities, that is, velocities relative to the smooth Hubble expansion, show coherent patterns of infall toward dense concentrations of mass. The definition of a supercluster is therefore partly geometric based on the spatial distribution of galaxies and clusters, and partly dynamical based on the inferred flows of matter and the depth of the underlying gravitational potential. Numerical simulations that follow the growth of structure in a universe dominated by dark matter and dark energy naturally produce supercluster scale features as part of the cosmic web. In these simulations, multiple cluster-sized dark matter halos form along major filaments and within larger overdense patches. The halos continue to accrete material from surrounding filaments and to merge with one another over billions of years, while the filaments themselves feed gas and smaller halos into the growing structures. The resulting configurations resemble observed superclusters, with chains of clusters and groups extending across hundreds of millions of light-years and embedded in more diffuse distributions of galaxies and gas. Superclusters mark regions where structure formation has progressed further than average, but has not necessarily reached complete gravitational collapse on the larger scale of the region. Within a supercluster, individual galaxy clusters can be fully virialized, meaning that their internal motions and mass distribution satisfy approximate dynamical equilibrium, while the relative motions among different clusters still reflect ongoing evolution and infall along filaments. In the nearby universe, detailed studies of supercluster environments show that the properties of galaxies and clusters can depend on their position within the larger structure. Clusters near the dense core of a supercluster can have higher galaxy densities, richer populations of massive galaxies, and more heated intracluster gas than clusters located in the outskirts or along connecting filaments. Galaxies that reside in supercluster cores are more likely to be massive ellipticals with older stellar populations and lower current star formation, while galaxies in lower density regions such as filaments and the edges of superclusters often show a higher fraction of spiral morphologies and ongoing star formation. This pattern follows the general trend that denser environments tend to host more quenched early-type galaxies, and that environment can influence galaxy evolution through mechanisms such as gas stripping, tidal interactions, and the cumulative effects of residing in massive halos and dense surroundings. For galaxy clusters embedded in superclusters, the large-scale context can also affect their growth histories. Clusters in supercluster nodes may experience more frequent mergers with other groups and clusters, as well as higher rates of accretion of matter along filaments. These processes can build up the mass of the cluster. Dark matter halo increase the amount of hot intracluster gas and shape the distribution and kinematics of galaxies within the cluster. Observationally, such effects are studied by comparing the mass functions, X-ray properties and galaxy populations of clusters in supercluster environments with those of more isolated clusters. Differences in these quantities provide insight into how large-scale structure influences cluster formation and evolution. The identification of superclusters in observational data involves algorithms that link galaxies or clusters according to their positions and sometimes velocities, for example using friends of friends techniques or density field reconstructions. By applying these methods to wide field surveys, astronomers map out the skeleton of the nearby universe, identifying the most massive superclusters and studying their internal structures. Some of these systems host particularly rich cluster concentrations that serve as key laboratories for understanding high-density environments. Others form elongated chains that stretch across large parts of the sky, indicating the presence of extended filaments of matter. In this framework, any given galaxy cluster can be viewed both as a bound structure in its own right and as part of a larger supercluster scale configuration that provides its cosmological setting. The gravitational potential of the supercluster region influences the motions of its member clusters and groups, while the clusters themselves define the deepest local wells where galaxies' gas and dark matter have collapsed. The surrounding filaments connect these clusters to one another and to the wider cosmic web, channeling matter into the supercluster region over long timescales. Studies of superclusters therefore complement detailed investigations of individual clusters by placing them in a context that extends hundreds of millions of light-years, and by linking their internal properties to the patterns of structure on the larger scales observable in the local universe. Measurements of how many superclusters of a given richness exist, how their clusters are distributed, and how their matter content compares with predictions from cosmological simulations also allow tests of cosmological parameters and of the rate at which structures have grown over cosmic time. In this way, supercluster studies connect local observations of galaxies and clusters to the broader framework of cosmology and to the physics of the evolving universe. By considering superclusters in combination with other cosmological probes such as the cosmic microwave background and large-scale galaxy clustering, astronomers build a consistent picture of how matter is arranged and how structures like clusters emerge within that arrangement. On the scale of the nearby universe, astronomers map the positions and motions of galaxies out to hundreds of millions of light-years to understand how local structures emerge from the cosmic web. Within this volume, the Milky Way and its local group occupy a modest region, embedded in a network of filament sheets and voids that continues outward to more massive nodes where galaxy clusters reside. One such node lying in the direction of the constellation, Leo, is known as the Leo cluster, a concentration of galaxies at a distance of roughly several hundred million light-years from Earth. Redshift measurements, which record how much the spectral lines of galaxies are shifted toward longer wavelengths by cosmic expansion, provide the primary tool for estimating this distance. By combining these redshifts with models of the expansion history of the universe, astronomers infer that the Leo cluster belongs to the population of relatively nearby clusters that can be studied in detail with current optical and X-ray observatories. In three-dimensional maps constructed from galaxy redshift surveys, the Leo cluster appears as a dense grouping of galaxies located along a larger filament that extends across a substantial part of the sky in the Leo region. This filament links the cluster to neighboring groups and less massive clusters, while more diffuse galaxies trace bridges between these systems and out into surrounding lower density regions. The local flow of galaxies obtained by subtracting the smooth Hubble expansion from observed velocities indicates that matter in this region experiences gravitational attraction towards several major mass concentrations, including clusters and supercluster cores. The Leo cluster participates in these flows, contributing its own gravitational field and responding to the potentials of larger-scale structures. Its position in redshift space and on the sky suggests that it is part of a broader association of clusters and filaments that share a common large-scale environment, although the precise boundaries and dynamical status of this association depend on the criteria used to define a supercluster. Because the Leo cluster is located at a distance that is large compared with the size of individual galaxies, but small compared with the scale of the observable universe, it occupies a useful regime for detailed observation. At this distance, individual bright galaxies can be resolved and studied with ground-based telescopes, and their internal stellar distributions and kinematics can be probed with high-resolution spectroscopy. Space-based observatories add information on faint stellar halos, central regions, and compact sources. X-ray telescopes detect the hot intracluster gas that fills the deep gravitational potential well of the cluster, while radio observations can reveal synchrotron emission from relativistic particles accelerated in shocks and around active galactic nuclei in member galaxies. Together, these data allow a comprehensive view of the baryonic components of the cluster, that is, of the normal matter in the form of stars, gas, and dust, and provide indirect constraints on the dark matter halo that dominates the cluster mass. Relative to very distant clusters seen when the universe was much younger, the Leo cluster represents a more evolved state of structure formation, in which many of the largest galaxies have already assembled most of their mass, and the intracluster medium has been heated to high temperatures through gravitational processes and feedback from galaxies. At the same time, the cluster continues slowly to accrete matter from surrounding filaments, as suggested by the distribution of infalling groups and the presence of galaxies on elongated orbits that have not yet fully mixed into the cluster core. The motions of galaxies within and around the cluster, measured through their line-of-sight velocities, provide estimates of the total cluster mass through dynamical methods that assume approximate virial equilibrium in the central regions. Independent mass estimates come from X-ray measurements of the intracluster gas, whose density and temperature profiles depend on the depth of the potential well, and from gravitational lensing in which the mass of the cluster distorts the paths of light from more distant background sources, producing subtle image distortions that can be analyzed statistically. For the Leo cluster, these techniques indicate a total mass typical of a rich galaxy cluster, with most of that mass in dark matter, a significant fraction in hot gas, and a smaller fraction in stars bound to galaxies and diffuse intracluster light. The environment around the cluster, traced by the spatial distribution and properties of nearby galaxies, shows transitions from the dense, hot, and dynamically active core to cooler, less dense outskirts, where galaxies are beginning to feel the influence of the cluster potential. In these outer regions, environmental effects such as gas stripping and tidal interactions begin to modify the gas content and morphology of galaxies, gradually transforming some of them from gas-rich spirals with active star formation into gas-poor systems with lower star formation rates. Closer to the core, the galaxy population is dominated increasingly by massive older systems, many of them ellipticals that trace the deepest part of the cluster potential. Taken together, these observations place the Leo cluster within the landscape of the nearby universe as a substantial node in the network of matter, located at a distance that permits detailed study and embedded in a web of filaments and surrounding structures that continue to supply it with material over long time scales. The Leo cluster can be described as a gravitationally bound system of galaxies, hot gas and dark matter, occupying a region of space with a characteristic size of a few to several million light-years across, within which the motions of member galaxies are dominated by the common cluster potential, rather than by the general expansion of the universe. In practice, astronomers delineate the cluster by combining information on galaxy positions on the sky, redshifts and line-of-sight velocities to distinguish galaxies that are dynamically associated with the cluster from foreground and background objects that happen to lie along the same line of sight. The cluster shows a central concentration of galaxies where the projected number density rises strongly compared with surrounding fields, and the velocity distribution of these galaxies forms a relatively well-defined peak around a mean redshift that corresponds to the cluster distance. The dispersion of velocities around this, mean often of the order of many hundreds of kilometers per second, reflects the depth of the gravitational potential well and allows estimates of the total mass enclosed within a given radius when combined with assumptions of dynamical equilibrium. In the Leo cluster, as in other rich clusters, the total gravitating mass inferred from galaxy motions far exceeds the mass that can be accounted for by luminous matter alone, implying the presence of a dominant dark matter component that extends well beyond the visible extent of the galaxies. The spatial distribution of galaxies in the Leo cluster shows a roughly centrally concentrated profile with a dense core region and a more extended population of galaxies in the outskirts. This profile can be characterized statistically by radial number density functions that decrease with increasing distance from the center, sometimes with substructure reflecting the presence of infalling groups or past mergers. The brightest galaxies are more strongly concentrated toward the center, and the central region typically hosts one or more very luminous ellipticals that occupy the deepest part of the potential well. Fainter galaxies, including dwarf ellipticals and small late-type systems, are distributed more widely, but still trace the cluster potential. The mix of galaxy morphologies within the Leo cluster follows the general trend seen in rich clusters with a high fraction of early-type galaxies, particularly in the core, and a smaller fraction of late-type star-forming galaxies that are more common in the outskirts and infall regions. The intracluster medium provides an independent tracer of the cluster structure. X-ray observations reveal hot diffuse gas at temperatures of tens of millions of degrees, filling the space between galaxies and approximately following the gravitational potential set by the dark matter halo. The surface brightness profile of this X-ray emitting gas, combined with spectral measurements of its temperature and metal abundances, constrains the gas density distribution and total gas mass. Under the assumption of hydrostatic equilibrium, in which the pressure gradient of the gas balances the gravitational pull, these profiles can be used to estimate the total mass as a function of radius. In the Leo cluster, as in other systems of similar richness, the gas mass is a substantial fraction of the total baryonic mass, and its radial profile provides evidence for a deep and extended dark matter halo encompassing the cluster. The agreement between mass estimates derived from galaxy dynamics and from X-ray gas analysis within uncertainties supports the interpretation of the Leo cluster as a largely virialized structure in its core, though the outer regions may still be in the process of accreting matter. Gravitational lensing offers a further test of the mass distribution. Even when strong lensing features such as giant arcs are not prominent, the statistical distortion of shapes of background galaxies known as weak lensing can be measured over wide fields and used to reconstruct the projected mass distribution. For a cluster at the distance of the Leo system, high-quality imaging from large ground-based telescopes or space-based observatories can detect these subtle shape distortions. The resulting mass maps generally show a central peak aligned with the galaxy density maximum, and extended halos consistent with expectations from dark matter-dominated cluster models. In some clusters, lensing reveals substructure associated with merging subclusters or groups. Similar analyses for the Leo cluster can identify any such features and quantify the degree of relaxation of the system. The overall richness of the Leo cluster, defined by the number of galaxies above a given luminosity threshold within a specified radius, places it among the more massive clusters in the nearby universe, though not at the extreme high end of the cluster mass function. Its galaxy population gas content and total mass indicate that it has undergone a long history of accretion and merging typical of structures that form at the intersections of filaments in the cosmic web. Comparison of its properties with those of other clusters at similar redshifts shows that, While individual details differ, the Leo cluster fits within the general scaling relations observed for clusters such as the relation between X-ray temperature and mass, or between galaxy velocity, dispersion, and total mass. These relations arise because the depth of the gravitational potential well sets characteristic speeds for galaxy motions and characteristic temperatures for shocked gas as it falls into the cluster. The internal structure of the Leo cluster can also be described in terms of characteristic radii, such as the radius within which the mean density is a fixed multiple of the critical density of the universe. Within these radii, the cluster is approximately gravitationally bound and dynamically relaxed. Outside them, the transition towards surrounding filaments and the larger scale structure becomes apparent with galaxies and groups moving on more radial orbits as they fall into the cluster for the first time. The analysis of the phase space distribution of galaxies combining positions and velocities allows astronomers to identify infall regions, caustic boundaries, and possible remnants of past subcluster mergers. In the Leo cluster, such studies indicate that while the central region is relatively relaxed, consistent with a long timescale, since the last major merger, there remain groups and individual galaxies on high-velocity orbits that trace ongoing accretion. The interplay between the intra-cluster medium and cluster galaxies provides further evidence of the cluster-scale environment. Galaxies moving through the dense central gas at high relative speeds experience ram pressure that can strip their own gas, reducing their ability to form new stars and contributing additional material to the intracluster medium. Observations of truncated gas disks, disturbed gas morphologies, and tails of stripped material in some cluster galaxies support this picture. Over time, these processes contribute to the transformation of spiral galaxies into more gas-poor systems and enhance the dominance of early-type galaxies in the core. In the Leo cluster, the balance between such processes, tidal interactions among galaxies and internal galaxy evolution, shapes the observed mix of galaxy types and star formation activity. Thus, when considered as a whole, the Leo cluster presents a coherent structure in which galaxies' hot gas and dark matter are tied together by gravity with internal properties that reflect both the depth of the potential well and the long history of assembly from smaller scale components. The galaxy population of the Leo cluster provides a detailed view of how galaxies are distributed and transformed in a dense cluster environment. When astronomers survey this cluster in optical light infrared and other bands, they find that its member galaxies span a range of luminosity sizes and morphologies, where morphology refers to the visible structural type of a galaxy, such as an elliptical system with a smooth stellar distribution, or a spiral system with a disk and spiral arms. A common way to describe the population is through the luminosity function, which expresses how many galaxies there are at each luminosity. In rich clusters like the Leo system, this function typically shows a relatively small number of very luminous galaxies, a larger number of intermediate galaxies, and a still larger population of low luminosity dwarf systems. The brightest galaxies are usually massive ellipticals centrally concentrated in the cluster core, while dwarf ellipticals and other low-mass systems are found both in the core and in the outskirts. Spiral galaxies, which are common in the field and in lower density environments, are present in the Leo cluster, but with a reduced fraction compared with the cosmic average, particularly toward the dense central regions. The dominance of early-type galaxies, meaning ellipticals and lenticulars, with little or no visible spiral structure, reflects the effects of the cluster environment on galaxy evolution over long time scales. To characterize these trends, astronomers construct color magnitude diagrams which plot galaxy brightness against color, and find that many cluster galaxies lie along a tight red sequence, corresponding to systems with older stellar populations and low current star formation, while a smaller population occupies a bluer region associated with ongoing star formation. In the Leo cluster, as in other rich clusters, the red sequence is well populated, especially at high luminosities, indicating that many of the most massive galaxies have assembled their stars early, and have since evolved passively, with only modest subsequent star formation. The blue cloud of star-forming galaxies is more prominent at lower luminosities, and in the outskirts where environmental effects are weaker. Spectroscopic observations which measure the detailed shapes and strengths of absorption and emission lines in galaxy spectra provide further insight into stellar ages, metallicities, and star formation histories. Elliptical galaxies in the Leo cluster generally show spectral features consistent with old metal-rich stellar populations, while some spirals and irregular galaxies exhibit emission lines indicating ongoing formation of massive short-lived stars. The spatial distribution of different morphological types within the Leo cluster follows a morphology-density relation in which early-type galaxies dominate the regions of highest projected galaxy density, particularly near the cluster center, and late-type galaxies are more common at lower densities in the outskirts and along infall regions. This relation suggests that processes associated with the dense cluster environment either transform galaxies from late-type to early-type morphologies, or preferentially quench star formation in galaxies that reside for long periods in the core. Mechanisms that contribute to such transformations include ram pressure stripping, where the interstellar gas of a galaxy is removed by the pressure of the hot intracluster medium as the galaxy moves at high speed through the cluster, and galaxy harassment, a term used to describe repeated high-speed encounters with other galaxies, and with the cluster potential that can disturb a galaxy's structure. Tidal interactions and mergers, especially in subgroups and in the cluster outskirts where relative velocities are lower, can also alter galaxy morphology and star formation, sometimes triggering bursts of star formation before gas is exhausted or removed. Over the lifetime of the cluster, these processes gradually change the balance of galaxy types, increasing the fraction of gas-poor quiescent systems in the higher density regions. Dwarf galaxies form an important component of the Leo cluster population. These low-mass systems, including dwarf ellipticals and dwarf spheroidals, are numerous and contribute significantly to the total galaxy count, though only a modest fraction of the stellar mass. Their structural and kinematic properties are sensitive to environmental effects, and many show signs of tidal truncation or disturbed outer regions indicating past interactions with the cluster potential or with more massive galaxies. Some dwarf systems retain small amounts of gas and residual star formation, particularly in the outskirts, while those deep in the potential well are often gas-poor and dominated by older stars. The prevalence and properties of dwarfs in the Leo cluster can be compared with those in less dense environments to probe how the cluster environment shapes low-mass galaxies. The global kinematics of cluster galaxies derived from their line-of-sight velocities show that different subpopulations can have slightly different velocity dispersions and spatial distributions. For example, early-type galaxies concentrated in the core may have a velocity distribution closer to dynamical equilibrium, while late-type galaxies and recently accreted dwarfs may exhibit broader or more asymmetric velocity distributions, reflecting their incomplete mixing into the cluster potential. By analyzing these patterns, astronomers can infer aspects of the assembly history of the Leo cluster, including the rate at which groups and field galaxies are still being incorporated. Observations sometimes reveal substructures in position velocity space that correspond to infalling groups or remnants of recent mergers, which gradually dissolve as galaxies orbit within the cluster, and their orbits are randomized by the overall potential. Multi-wavelength studies further refine the picture of the Leo cluster galaxy population. Infrared observations trace older stellar populations and can reveal galaxies whose optical light is heavily reddened by dust, while ultraviolet data highlight regions of recent star formation. Radio observations detect neutral hydrogen gas and molecular gas through characteristic spectral lines and continuum emission, providing a direct measure of the cold gas reservoirs that fuel future star formation. In the Leo cluster, neutral hydrogen surveys often show that many central galaxies are gas-depleted compared with similar mass galaxies in the field, supporting the view that RAM pressure stripping and other gas removal processes are efficient in the dense intracluster medium. Some galaxies exhibit extended radio emission associated with jets and lobes powered by active galactic nuclei, indicating the presence of accreting supermassive black holes that can inject energy into the surrounding gas and influence both the host galaxy and on larger scales the intracluster medium. Taken together, the luminosity distribution morphological mix, spectral properties, kinematics and gas content of the Leo cluster galaxies present a consistent view of a mature cluster environment. Massive early-type galaxies populate the central regions, tracing the deepest parts of the gravitational potential, while a mix of spirals, lenticulars and dwarfs extends into the outskirts and along connecting filaments. Environmental processes specific to the cluster scale, combined with the internal evolution of galaxies, have produced a population in which old quiescent systems are common in the core, and active gas-rich systems are more common in lower density regions. This structured galaxy population provides essential context for understanding the formation and present state of the most luminous members of the cluster and their relationship to the overall cluster environment. The hot gas and dark matter of the Leo cluster together define its large-scale gravitational and thermodynamic structure, and they account for most of the mass and energy in the system beyond the stars of the member galaxies. The hot gas, known as the intracluster medium, consists mainly of ionized hydrogen and helium with trace amounts of heavier elements that have been produced in stars and ejected by supernovae and galactic winds. This gas reaches temperatures of tens of millions of degrees, so that it emits strongly in X-rays through thermal bremsstrahlung and line emission from highly ionized metals. X-ray observations of the Leo cluster therefore provide direct measurements of the gas temperature, density and metallicity as a function of position, and they reveal a diffuse glow that approximately traces the shape of the underlying gravitational potential well. The surface brightness of the X-ray emission falls with increasing radius from the cluster center, reflecting the decline in gas density, while variations in temperature and metal abundance encode information about past heating events, cooling processes, and the enrichment history of the cluster. Under the assumption that the gas is close to hydrostatic equilibrium, in which the pressure gradient balances the gravitational acceleration at each radius, the observed density and temperature profiles can be combined to infer the total mass profile of the cluster. This method shows that the gas mass is a significant fraction of the total baryonic content, but still small compared with the total gravitating mass, which is dominated by dark matter. Dark matter in the Leo cluster is inferred from several lines of evidence. First, the velocities of member galaxies with dispersions of many hundreds of kilometers per second require a deep gravitational potential. Well, if the system is to be gravitationally bound, the virial theorem applied to the galaxy population yields a total mass well in excess of the mass that can be accounted for by the observable stars and gas. Second, the hydrostatic analysis of the intracluster medium, which is independent of the galaxy dynamics, leads to similar mass estimates over a wide range of radii, reinforcing the conclusion that most of the mass is in a non-luminous component. third gravitational lensing measurements, which do not depend on assumptions of dynamical equilibrium, show that the Leo cluster, like other rich clusters, distorts the images of background galaxies in a way that corresponds to a massive extended dark matter halo. These three methods, based on galaxy motions, gas properties and lensing, converge on a consistent picture in which dark matter outweighs baryonic matter in the cluster by a large factor and extends far beyond the visible edges of the galaxy distribution. The radial distribution of dark matter in the Leo cluster can be described by profiles that are similar to those found in cosmological simulations of structure formation with cold, dark matter. These simulations predict that dark matter halos have density profiles that are steep in the center and shallower in the outskirts, with characteristic scale radii that depend on the halo mass and formation history. When such profiles are fitted to the combined dynamical X-ray and lensing data for the Leo cluster, they reproduce the observed mass distribution reasonably well, though detailed fits can reveal deviations associated with substructures, mergers, or non-thermal pressure support in the gas. The central region often shows a slight excess of mass associated with the brightest cluster galaxy and its own dark matter sub-halo superimposed on the broader cluster halo. At intermediate radii, the gas and galaxy density profiles trace the dark matter potential in a smoothed way, while at large radii the density falls toward the level of the surrounding filaments and the cosmic mean. The intracluster medium shows additional structure beyond the smooth radial trends. Temperature maps derived from spatially resolved X-ray spectroscopy can reveal asymmetries, shocks, and cold fronts that are signatures of past or ongoing mergers, sloshing motions of the gas in the potential well, or the impact of energy input from active galactic nuclei. In the Leo cluster, temperature gradients and possible local disturbances can indicate whether the cluster core is relaxed and cooling steadily, or whether it has been recently perturbed. Clusters with so-called cool cores show central regions where the gas temperature drops and the density rises, leading to short radiative cooling times. In the absence of heating, such regions would experience substantial cooling flows, but observations indicate that cooling is partly offset by energy input, likely from jets, and outflows driven by the supermassive black holes in central galaxies. In non-cool core clusters, mergers and large-scale motions can disrupt such structures and distribute energy more uniformly. The state of the intracluster medium in the Leo system, whether closer to a cool core or non-cool core regime, informs models of how feedback from galaxies and black holes regulates gas cooling and star formation in the densest environments. The chemical composition of the intracluster gas provides further clues to cluster evolution. Measurements of elemental abundances such as iron, silicon, and oxygen show that the gas has been enriched by multiple generations of stars in cluster galaxies. Supernova explosions eject metals into the interstellar medium, which are later transported into the intracluster medium through galactic winds, ram pressure stripping, and tidal interactions. The observed abundance patterns and their radial variation can be compared with models of chemical enrichment to infer the relative contributions of different supernova types and the history of star formation in the cluster. Typically, abundances are highest near the cluster center, where the dense old galaxy population is concentrated, and decrease with radius, reflecting the cumulative effect of enrichment and mixing over time. The dark matter halo influences these processes by setting the depth of the potential well that holds the gas and by determining how easy it is for galactic winds to escape or for stripped gas to be retained. On large scales, the dark matter and gas together define the cluster potential that governs the orbits of galaxies and the flow of infalling material. Along filaments that connect to the Leo cluster, warm hot gas continues to supply the cluster with baryons, some of which are shock-heated as they cross the virial radius. This process maintains the intracluster medium and slowly increases its mass. At the same time, the dark matter halo grows through accretion of smaller halos and merges with other groups and clusters as predicted by hierarchical structure formation scenarios. As the halo mass increases, the characteristic temperature and entropy of the intracluster gas adjust to the deeper potential well-following scaling relations that link mass temperature and X-ray luminosity in cluster populations. The Leo cluster, with its particular mass and environment, occupies a specific point on these relations, providing one data point among many that collectively test the physics implemented in cosmological simulations. Small deviations from the expected scaling can point to the importance of non-gravitational processes, such as feedback and non-thermal pressure support from turbulence or cosmic rays. In summary, the hot intracluster gas and the dominant dark matter halo of the Leo cluster form a coupled system where gravity sets the overall structure and depth of the potential well, while gas dynamics, radiative cooling and energy input from galaxies and active nuclei shape the thermodynamic state of the baryonic component. The stars in the cluster galaxies contribute only a modest fraction of the total mass, but through their evolution, they enrich the gas and modulate its cooling behavior. The combined analysis of these components provides a quantitative framework for understanding the Leo cluster as a massive dark matter-dominated system embedded in the cosmic web and evolving slowly under the combined influence of gravity and baryonic physics. NGC 3842 is identified as the brightest cluster galaxy of the Leo cluster, occupying a central position in the projected galaxy distribution and lying close to the minimum of the cluster gravitational potential. As a brightest cluster galaxy, it is among the most luminous and massive stellar systems in the cluster, with an extended stellar envelope that blends gradually into the diffuse intracluster light. In optical images, NGC 3842 appears as a smooth, nearly featureless elliptical system whose surface brightness decreases monotonically with radius, showing no prominent spiral arms bars or other disk-like structures. Its light distribution is often described by empirical profiles that approximate how the surface brightness falls with distance from the center, and these fits indicate a large effective radius, meaning that half of the total light is contained within a region that spans many tens of thousands of light years. Compared with typical field ellipticals of similar luminosity, brightest cluster galaxies like NGC 3842 often exhibit more extended outer envelopes, sometimes referred to as CD-type halos, which reflect the accumulation of stars from disrupted satellites and past mergers. The position of NGC 3842, at or near the geometric and dynamical center of the Leo cluster, is inferred from the concentration of surrounding galaxies and from the approximate symmetry of the intracluster X-ray emission around it. The galaxy's systemic velocity, measured from the redshift of its integrated stellar spectrum, lies close to the mean velocity of the cluster, consistent with its location in the deepest part of the potential well. This central role suggests a long history of interactions in which NGC 3842 has grown through mergers with other galaxies and through the gradual accretion of stars and gas drawn in by dynamical friction and tidal stripping. Numerical simulations of cluster formation support this picture, showing that central galaxies in massive halos accumulate mass in part through early intense episodes of star formation and in part through later mergers with satellite galaxies that sink toward the center over billions of years. The stellar population of NGC 3842, as inferred from its colors and absorption line spectra, is dominated by old stars with relatively high metal abundances. This indicates that most of its stars formed at early cosmic times when gas densities were higher and star formation rates in massive halos were elevated, and that subsequent chemical enrichment by supernovae has raised the heavy element content of the stars to levels above those in less massive galaxies. The integrated light is generally red, consistent with a population of evolved low-mass stars, and there is little evidence for recent large-scale star formation. Any residual star formation that might occur would be at a low level, and possibly confined to small regions, contributing only modestly to the total luminosity. Infrared observations further support the dominance of old stellar populations, and show that dust content is low compared with that in star-forming spirals. The kinematics of stars in NGC 3842 provide key constraints on its mass distribution. Long-slit spectroscopy and integral field spectroscopy measure the broadening and shifting of stellar absorption lines across the galaxy, yielding line-of-sight velocity dispersions and rotation patterns as functions of radius. In massive ellipticals like NGC 3842, velocity dispersions in the central regions can reach several hundreds of kilometers per second, reflecting the deep gravitational potential of the combined stellar and dark matter mass. The observed kinematic profiles can be compared with dynamical models that incorporate the stellar mass distribution, a dark matter halo, and a central mass component, allowing estimates of the mass-to-light ratio of the stellar population and the shape of the dark matter profile in the inner galaxy. In brightest cluster galaxies, the contribution of dark matter to the total mass within the effective radius is often significant, though the stellar component dominates the light. At larger radii, the potential gradually transitions from being dominated by the galaxy halo to being dominated by the cluster halo, and stellar kinematics can probe this transition region. The structure of NGC 3842 also includes a central light profile that may deviate from a simple extrapolation of the outer profile. High-resolution imaging from space-based telescopes can resolve the inner few hundred parsecs, revealing whether the brightness rises steeply or shows a flattened core. In many massive ellipticals, the central surface brightness profile exhibits a core, a region where the density of stars is lower than expected from the outer trend. Such cores are thought to result from dynamical processes associated with the evolution of binary supermassive black holes, which can eject stars from the central regions through gravitational interactions as they harden and eventually coalesce. The present size and shape of a core in NGC 3842 therefore provide information about its merger history and the evolution of its central regions. Surrounding NGC 3842, the extended stellar envelope merges into the intracluster light, a diffuse component composed of stars that are no longer bound to individual galaxies but orbit in the overall cluster potential. This light can be detected as low surface brightness emission that follows the central regions of the cluster and often extends along directions where tidal interactions and mergers have been frequent. The fraction of total cluster light in this diffuse component provides a measure of the cumulative impact of galaxy interactions over the lifetime of the cluster. In the case of the Leo cluster, NGC 3842 contributes a large share of the total stellar luminosity in the core, and its outer halo plays a central role in defining the appearance of the intracluster light. Observations of planetary nebulae and globular clusters associated with NGC 3842 and its surroundings offer complementary traces of the stellar distribution and kinematics at large radii. These discrete objects can be observed individually, and their velocities used to extend dynamical studies of the galaxy to distances where the surface brightness is too low for integrated light spectroscopy. Globular cluster systems around brightest cluster galaxies are often rich and extended with thousands of clusters, distributed over hundreds of thousands of light years. Their spatial distribution colors and kinematics encode information about the assembly history of the host galaxy. In NGC 3842, the properties of its globular cluster system, when measured, can be compared with those of other central galaxies to place it within the broader context of cluster galaxy evolution. The environment immediately around NGC 3842 within the Leo cluster core shows an enhanced density of satellite galaxies and tidal features, such as streams and shells that point to ongoing and past accretion events. Deep imaging sometimes reveals arcs, plumes, or other low-surface brightness structures in the stellar halo produced when smaller galaxies are disrupted by tidal forces and their stars are distributed along their orbits. These features are transient on timescales of several orbital periods, but can persist long enough to record recent merger activity. The presence or absence of such structures around NGC 3842 helps constrain the recent mass accretion rate and the dynamical state of the core. On the larger scales accessible within the cluster, the positioning and properties of NGC 3842, its extended halo and the surrounding galaxy population collectively identify it as the central dominant galaxy of the Leo cluster, linking the luminous baryonic component directly to the deepest part of the cluster's dark matter potential. On the scale of an individual galaxy, NGC 3842 can be described quantitatively by its overall structure size and luminosity distribution properties that place it among the most massive known elliptical systems in the nearby universe. Observationally, its stellar light is mapped in optical and near-infrared bands, where long exposure images reveal a smooth, nearly elliptical pattern of isophotes, the contours of constant surface brightness. These isophotes are close to concentric and show only mild deviations from perfect ellipses, indicating that the galaxy lacks strong disk-like components or large-scale asymmetries. The projected axial ratio derived from the apparent flattening of the isophotes suggests that NGC 3842 is only moderately flattened on the sky, consistent with a three-dimensional structure that is triaxial or nearly spheroidal. The surface brightness profile, which records how the intensity of light decreases with increasing radius from the center, is well fitted over a wide radial range by a Sérsic-type law, an empirical function used to describe the radial distribution of light in galaxies. For giant ellipticals like NGC 3842, the Sérsic index is typically higher than in less massive systems, reflecting a more strongly peaked central profile and extended outer wings. The effective radius defined as the radius that encloses half of the total projected light reaches values of many tens of thousands of light years, confirming that the stellar body of NGC 3842 spans a scale that is large even by the standards of massive ellipticals. Beyond this radius, the profile declines gradually into the low surface brightness outskirts, where the distinction between the galaxy halo and the surrounding intracluster light becomes increasingly a matter of definition and observational depth rather than a sharp physical boundary. Photometric studies of NGC 3842, which measure its brightness and color as functions of radius, indicate mild gradients in color, with the central regions appearing slightly redder than the outskirts. Such gradients are commonly interpreted as signatures of changes in stellar metallicity, or age with higher metallicity or older populations concentrated toward the center. In massive ellipticals, these gradients often result from the combined effects of dissipative processes during early star formation, which can concentrate metal-enriched gas toward the core, and later accretion of lower-mass satellites that contribute somewhat more metal-poor stars to the outskirts. For NGC 3842, the observed gradients are consistent with the picture in which the bulk of the central stellar mass formed early, and was enriched to relatively high metallicity, while the outer regions assembled partly through the accretion of smaller systems over extended timescales. Integrated photometry yields total luminosities in various bands that, when combined with stellar population models and estimates of the mass-to-light ratio, imply a total stellar mass that is very large compared with typical field galaxies, placing NGC 3842 among the most massive central galaxies in nearby clusters. The distribution of stellar mass inferred from the light profile can be converted into a three-dimensional density profile under reasonable assumptions about the intrinsic geometry. This profile shows that the stellar density declines steeply with radius, with the central regions containing a significant fraction of the total mass in a relatively small volume, and the remainder distributed over the extended envelope. When this stellar density profile is combined with an assumed or modeled dark matter halo profile, one obtains the total mass distribution that governs stellar motions. In the inner few effective radii, the stellar component provides a major contribution to the gravitational potential, while at larger radii the dark matter contribution becomes progressively more important. The global kinematic structure of NGC 3842 complements these photometric measurements. Spatially resolved spectroscopy reveals that the velocity dispersion of stars remains high across a broad radial range, indicating that random motions rather than ordered rotation provide the main support against gravity. Any net rotation that is present is modest compared with the overall velocity dispersion, so that the galaxy is classified as a slow rotator in kinematic schemes that distinguish between rotation-dominated and dispersion-dominated early-type galaxies. This slow rotation is typical of the most massive ellipticals and suggests a merger history dominated by dissipationless events in which stellar systems combine without large amounts of cold gas to form new stars. The anisotropy of stellar velocities, meaning the relative importance of radial and tangential components, can be constrained by comparing observed kinematic profiles with dynamical models. In NGC 3842, the data favor a configuration in which stellar orbits are mildly anisotropic, with neither purely radial nor purely tangential motions dominating, and with the anisotropy varying gradually with radius. These structural and kinematic properties place NGC 3842 on global scaling relations for early-type galaxies, such as the fundamental plane which links effective radius means surface brightness within that radius and central velocity dispersion. On this plane, more massive galaxies occupy regions corresponding to larger effective radii and higher velocity dispersions following a relatively tight correlation that reflects underlying regularities in how mass, light and dynamics are arranged. NGC 3842 lies toward the massive end of this sequence, consistent with its role as the brightest cluster galaxy. Its position on related relations such as those between stellar mass and velocity dispersion, or between luminosity and size, similarly marks it as a system in which the assembly of stellar mass and the depth of the potential well have reached extreme values among nearby galaxies. The outermost parts of NGC 3842, where the surface brightness falls to very low levels, provide further information about its structure and its connection to the cluster environment. Deep imaging can reveal whether the isophotes become more elongated or show twists in position angle at large, radii signatures that point to triaxiality or to the influence of the surrounding cluster potential. Subtle excesses of light above the extrapolation of a smooth Circic profile can indicate the presence of tidal debris or shells from past mergers, while a deficit could signal core scouring processes in the inner regions, though the latter are better constrained by high-resolution imaging of the central profile. In the case of NGC 3842, The general smoothness and symmetry of the large-scale structure suggest that any recent major mergers have been limited, or that sufficient time has passed for tidal features to fade below current detection thresholds, while smaller-scale accretion events and interactions continue to contribute stars to the extended halo and to the intracluster light. Taken together, the overall structure and size of NGC 3842, as quantified by its light distribution effective radius shape and kinematics, define it as a giant elliptical galaxy, whose stellar body dominates the luminous mass in the core of the Leo cluster, and whose spatial extent and mass place it among the most extreme products of galaxy assembly in the local universe. Stellar populations and the hot gas associated with NGC 3842 together describe how the galaxy forms and evolves within the core of the Leo cluster. The integrated light of NGC 3842 observed in optical and near-infrared bands is dominated by old stars which produce a smooth red continuum with absorption features characteristic of evolved low-mass stellar populations. Color measurements show that the galaxy lies firmly on the red sequence of cluster galaxies, with small scatter indicating that current star formation is very weak or absent on galaxy-wide scales. Spectroscopic studies that compare observed absorption line strengths with stellar population synthesis models infer typical stellar ages that are large compared with the age of the universe, at intermediate redshifts consistent with the bulk of star formation occurring at early cosmic times. The same analyses indicate relatively high metallicities, meaning that the heavy element content of the stars is greater than in the Sun, and often show enhanced ratios of alpha elements relative to iron, which suggest that early star formation proceeds rapidly, with enrichment dominated by core collapse supernovae, before type Ia supernovae contribute large amounts of iron. These patterns place NGC 3842 alongside other massive ellipticals whose stars form in intense brief episodes at high redshift, and then evolve passively with only modest subsequent star formation. Radial gradients in colors and absorption, line indices within NGC 3842, indicate that the central regions host slightly older or more metal-rich populations than the outskirts. This is consistent with models in which dissipative processes during early formation concentrate gas and star formation toward the center, while later accretion of smaller satellites adds somewhat more metal-poor stars to larger radii. The gradients are usually smooth rather than abrupt, suggesting that the transition between central and outer populations develops gradually through a combination of internal evolution and external accretion. The stellar population mix can also be probed through the distribution of globular clusters, which often divides into subpopulations with different colors and spatial distributions. In many brightest cluster galaxies, a metal, rich centrally concentrated globular cluster population coexists with a more extended metal-poor population. This pattern, when observed around NGC 3842, supports a picture in which part of the globular cluster system forms in situ in the deep potential of the main progenitor, while another part arrives with accreted satellites. Together, these stellar traces show that NGC 3842 is dominated by old metal-rich stars with a layered history in which early centrally concentrated star formation is followed by prolonged assembly of the outer halo. The hot gas directly bound to NGC 3842 forms a galactic scale atmosphere embedded within the larger intracluster medium of the Leo cluster. X-ray observations reveal an extended corona of hot diffuse gas centered on the galaxy, with temperatures of tens of millions of degrees comparable to, or slightly lower than, the surrounding intracluster gas. This gas emits X-rays through thermal processes and contributes to the overall X-ray luminosity of the cluster core, though it represents only a small fraction of the total gas mass in the cluster. The density of the galactic corona is higher near the center, and falls with radius merging smoothly into the properties of the surrounding intracluster medium. In some brightest cluster galaxies, the central gas shows cooler regions and higher densities that produce short radiative cooling times, raising the possibility that gas could cool and condense toward the center. However, observations of line emission at other wavelengths and the relatively low rates of star formation inferred from ultraviolet and optical data indicate that large, steady cooling flows are not present. Instead, some form of heating offsets most of the radiative losses. In the environment of NGC 3842, a likely source of such heating is mechanical energy injected by jets and outflows from an active galactic nucleus in the galaxy core, even if the nucleus is not currently radiating strongly across the electromagnetic spectrum. Radio observations in some similar systems detect jets and lobes that inflate cavities in the hot gas, and X-ray images show depressions in surface brightness that mark the locations of these cavities. When analogous features are present around NGC 3842, they indicate that feedback from the central engine acts on the surrounding gas and can regulate its cooling. The balance between radiative cooling and such feedback helps to maintain the low levels of ongoing star formation inferred from the stellar populations. The metal content of the hot gas around NGC 3842 also carries signatures of the integrated star formation and enrichment history of the galaxy. X-ray spectra show emission lines from highly ionized iron and other elements from which abundances can be derived. Typically, the gas near the galaxy center is more metal-rich than gas, at larger radii, reflecting the cumulative injection of metals by supernovae and stellar winds in the central stellar population. Over time, mixing processes including turbulence, buoyant motions driven by active galactic nucleus feedback and sloshing of gas in the cluster, potential distribute these metals outward, producing gradual abundance gradients. The presence of enriched gas in the galactic corona and in the surrounding intracluster medium demonstrates that a significant fraction of metals produced in stars do not remain locked in stellar atmospheres, but are transferred into the gaseous phase. This enriched gas in turn influences cooling rates and the formation of future generations of stars if and when cooling proceeds. The relative distributions of stars and hot gas in and around NGC 3842 show that the stellar component is centrally concentrated and dynamically cold compared with the highly extended high-temperature gas. Stars follow orbits determined largely by the gravitational potential of the combined stellar and dark matter mass, while the gas responds both to gravity and to pressure gradient shocks and heating processes. The ratio of gas to stellar mass within a given radius is low in the galaxy interior, rises toward the outskirts, where the intracluster medium dominates and reaches values typical of clusters at large radii. This arrangement is consistent with a scenario in which gas, that originally cools to form stars in the progenitors of NGC 3842, has largely been converted into stars or expelled, while the present hot atmosphere represents a combination of gas that has been heated by feedback processes and gas supplied by stellar mass loss and the inflow of intracluster medium. The hot gas thus records both the integrated stellar activity of NGC 3842 and its interaction with the cluster environment. By analyzing the stellar populations and the surrounding hot gas together, astronomers obtain a coherent view in which early rapid star formation builds up a massive metal, rich stellar body. Subsequent accretion and dynamical processes assemble the outer halo, and the current state of the hot gas reflects the balance between cooling and feedback in the deep potential well at the center of the Leo cluster. In the inner regions of NGC 3842, the distribution of starlight changes gradually from the extended halo that dominates large radii to a denser, more centrally concentrated structure in which the surface brightness rises steadily toward the core. Photometric measurements with ground-based and space-based telescopes trace this transition from scales of many tens of thousands of light-years down to scales of a few hundred light-years, revealing how the projected brightness profile steepens or flattens as the center is approached. When astronomers fit empirical functions to the radial surface brightness profile over this wide range of radii, they often find that a single fitting law does not describe the entire galaxy. Instead, there is usually a distinct change in slope at an inner break radius, within which the profile becomes shallower than the extrapolation of the outer Circic light component. This behavior classifies NGC 3842 as a core-type elliptical galaxy, in contrast to less massive systems that show power law cusps continuing to the smallest resolved radii. The core is defined by a relative deficit of light compared with what would be expected if the outer profile continued inward unchanged. This light deficit implies that stars have been removed from the very central regions or redistributed to larger orbits, leaving behind a central zone with lower stellar density than a simple extrapolation would predict. The size of the core, measured by the radius at which the profile transitions from the outer to the inner slope, is of the order of a few hundred parsecs a scale, that is small compared with the overall size of the galaxy, but large enough to be resolved clearly in high-resolution imaging. Within this radius, the isophotes remain smooth and nearly elliptical, with no strong evidence for a distinct nuclear disk or compact star cluster separate from the main body of the galaxy. The absence of a sharp nuclear component and the presence of a shallow central slope are consistent with dynamical models in which repeated interactions involving a central massive object and surrounding stars have modified the stellar distribution over long timescales. The total amount of light missing from the core when compared with an inward extrapolation of the outer profile can be translated into a stellar mass deficit that provides a quantitative measure of how many stars have been displaced from the center. In massive core ellipticals like NGC 3842, this mass deficit is often comparable to several times the mass of the central massive object, inferred from dynamical studies suggesting an intimate link between core formation and the growth and evolution of that object. The central surface brightness profile of NGC 3842, together with the measured core size and light deficit, therefore serves as an important diagnostic of its central dynamical history, even before detailed kinematic information is considered. Two-dimensional analyses of high-resolution images provide further detail on the inner structure. By fitting elliptical isophotes and examining residuals, astronomers test for the presence of subtle features such as isophote twists, changes in ellipticity or boxy and disky deviations near the center. In NGC 3842, these deviations are modest, indicating that the central regions are largely relaxed and lacking strong non-axis symmetric components. Any dust present is confined to small faint patches that have limited impact on the overall brightness distribution, and there is little evidence for bright compact star-forming regions or bars that would produce obvious substructure. This smoothness supports the view that the central stellar body has reached a relatively stable configuration under the influence of the combined gravitational field of the stars and the central massive object. The radial gradient in color, which becomes slightly bluer with increasing radius, persists into the inner regions, though the core itself often shows less pronounced gradients because the stars there have undergone more mixing. Spectral studies of the innermost arc seconds show line strength indices similar to those of the surrounding central regions, indicating that the stellar populations in the core are not dramatically different in age or metallicity from those at somewhat larger radii. This homogeneity suggests that the core is not the result of recent centrally concentrated star formation, but rather of dynamical processes acting on an already established stellar population. At the same time, the overall high metallicity and old age inferred for the central stars confirm that they form part of the early formed metal-rich component that dominates the mass of the galaxy. The gradual brightening of the surface brightness profile toward the center, interrupted only by the shallow core, corresponds to a steady rise in the three-dimensional stellar density as the radius decreases. Dynamical models that deproject the observed profile estimate the actual volume density of stars as a function of radius, showing that it increases by many orders of magnitude between the outskirts and the inner few hundred parsecs. Within the core radius, the density profile still rises inward, but more slowly than it would in the absence of a light deficit. This dense stellar environment defines the background in which the gravitational influence of the central massive object is embedded. At radii large, compared with its sphere of influence, stellar motions respond primarily to the combined mass of stars and dark matter, and the potential can be approximated by smooth, slowly varying functions. As one moves inward through the region where the surface brightness is climbing and the density is rising, the relative importance of the central mass increases. Even though the kinematic signature of this influence is not yet described at this stage, the photometric structure alone already indicates that the inner regions are shaped by processes that couple the evolution of the central object and the surrounding stars. The core, the shallow central slope, and the smooth but dense stellar distribution provide constraints that any dynamical model must satisfy when it attempts to reproduce the observed motions of stars and infer the properties of the unseen central mass. In this way, the gradual brightening of the galaxy toward its core and the detailed form of the central light profile form an essential link between large-scale structure and the small-scale gravitational environment at the heart of NGC 3842. In the inner regions of NGC 3842, measurements of stellar motions provide the primary observational tool for constraining the underlying gravitational potential on scales that span from several effective radii down to distances comparable with the size of the observed core. These measurements are obtained by taking spectra along slits placed across the galaxy, or more comprehensively by using integral field spectrographs that record a full spectrum at each position element within a two-dimensional field. In both cases, the light at each location is the sum of many unresolved stars moving with a range of velocities along the line of sight. Their motions broaden the absorption lines in the integrated spectrum, and by comparing the observed line profiles with templates constructed from stellar spectra, astronomers derive the line of sight velocity distribution at that position. The simplest description of this distribution is given by its mean velocity and its dispersion, the latter representing the width of the distribution and serving as a measure of the typical random speeds of stars along the line of sight. Higher order moments, which describe deviations from a purely Gaussian form, provide additional information about the orbital structure. By mapping these quantities as functions of position, one obtains two-dimensional fields of mean velocity and velocity dispersion that trace how stars move within the gravitational potential of NGC 3842. In massive ellipticals, these maps usually show relatively low levels of ordered rotation and high dispersions, indicating that random motions dominate. NGC 3842 fits this pattern with central velocity dispersions of several hundreds of kilometers per second and only modest rotation signatures, if any, along its major axis. The dispersion profile often peaks in the inner regions and declines gradually with radius, though the precise shape depends on the balance between the stellar mass distribution, any central mass concentration, and the contribution of the dark matter halo on larger scales. The observed kinematics can be approximated initially by simple models in which the galaxy is treated as a spherically symmetric system in dynamical equilibrium with stars following orbits in a smooth potential generated by the combined mass of stars and dark matter. In this framework, the Jeans equations which relate the stellar density velocity, dispersions, anisotropy, and gravitational potential provide a means of predicting the radial dependence of velocity dispersion for a given mass profile. However, real galaxies such as NGC 3842 are not perfectly spherical, and the orbital distribution can be anisotropic with different weights of radial and tangential motions. To account for this complexity, more general dynamical models are constructed using orbit superposition methods. In these models, a trial gravitational potential is specified, typically including contributions from a stellar mass component with a given mass-to-light ratio, a dark matter halo with a parameterized profile, and a central point-like mass that represents any compact object at the center. A large library of stellar orbits is then computed within this potential, spanning a wide range of energies and angular momenta. Linear combinations of these orbits are sought that reproduce as closely as possible both the observed light distribution and the spatially resolved kinematic constraints. By varying the parameters of the potential and repeating the fit, one can identify the combinations that best match the data, thereby inferring the mass-to-light ratio of the stars, the parameters of the dark matter halo, and the amount of central mass required by the observations. In the case of NGC 3842, such orbit-based models use kinematic data that extend from the central arc seconds, where the core is resolved outward to radii, where the influence of the dark matter halo becomes significant. This broad radial coverage is essential for separating the contributions of different mass components, because changes in the potential at small radii affect the kinematics primarily in the central regions, while the halo mass influences the dispersion and rotation at larger radii. The models also accommodate possible variations in orbital anisotropy with radius, since the relative contributions of radial and tangential orbits can alter the projected velocity dispersion profile even for a fixed mass distribution. For instance, stars on more radial orbits can produce higher dispersions at a given radius than stars on predominantly tangential orbits, so ignoring anisotropy can lead to biased mass estimates. By fitting both the dispersions and the higher order moments of the line-of-sight velocity distribution, the models reduce these degeneracies and yield a more reliable reconstruction of the orbital structure. The inner kinematics of NGC 3842 show that stars in the central few hundred parsecs move with very high random speeds, and the dispersion there exceeds what would be expected if the mass distribution followed the stellar light alone with a reasonable spatially constant mass-to-light ratio. This excess is robust against plausible variations in anisotropy, indicating that additional mass must be present in the central region to account for the observed motions. The radius over which this excess is detected when compared with the overall size of the galaxy is small, suggesting that the additional mass is concentrated very near the center. Outside this radius, the dispersion profile transitions smoothly to values that can be explained by the combined influence of the stellar mass and the slowly rising contribution of the dark matter halo. At even larger radii, the profile reflects the full potential of the galaxy and the inner portion of the cluster dark matter halo. By systematically comparing models with and without a central mass component, and exploring a range of stellar mass to light ratios and halo parameters, astronomers analyzing NGC 3842 find that models lacking a compact central mass fail to reproduce the highest observed dispersions in the innermost regions, without invoking implausibly strong radial anisotropy or other contrived configurations. In contrast, models that include a central mass component concentrated within a volume much smaller than the core radius provide a significantly better fit to the inner kinematics, while remaining consistent with the stellar light distribution and the outer velocity field. The magnitude of this central mass component is then constrained by the requirement that the model reproduces both the amplitude and the shape of the dispersion profile, and the measured higher-order moments as functions of radius. In this way, the detailed mapping of stellar motions in the inner galaxy, combined with dynamical modeling, yields strong evidence that the gravitational potential of NGC 3842 contains a compact, massive central component in addition to the extended distributions of stars and dark matter that dominate on larger scales. The evidence that NGC 3842 hosts a very massive central concentration of mass arises from combining its detailed stellar kinematics with its precisely measured light distribution, and from testing a series of dynamical models against these data. Starting from the observed surface brightness profile, astronomers reconstruct the three-dimensional stellar density under reasonable assumptions about the intrinsic geometry and mass-to-light ratio. This stellar density, together with a parameterized dark matter halo profile constrained by the outer kinematics, defines an initial model for the mass distribution that does not include any additional compact central component. When the Jeans equations or more general orbit superposition models are applied to this mass distribution, the predicted line-of-sight velocity dispersions in the inner regions of the galaxy fall significantly below the observed values, even when one allows for a range of orbital anisotropies. Attempts to reconcile the models with the data by increasing the stellar mass-to-light ratio run into conflicts with constraints from stellar population models, which link the mass-to-light ratio to the ages and metallicities inferred from the galaxy's spectrum. Similarly, increasing the central dark matter density to account for the high dispersions would require a dark matter profile that is sharply peaked on scales much smaller than the characteristic radii expected from cosmological simulations of cold dark matter halos. Such a configuration would be inconsistent with the broader halo properties inferred from the outer kinematics and from the intracluster medium. These discrepancies indicate that neither the stars nor the extended dark matter halo, even with generous parameter adjustments, can by themselves generate the depth of the potential required to match the observed stellar speeds in the innermost regions. To resolve this, dynamical models introduce an additional central mass component treated as effectively point-like on the scales resolved by the observations. Mathematically, this component is represented as a compact contribution to the gravitational potential, whose mass is a free parameter in the modeling. When this central mass is included, the predicted velocity dispersion profile in the inner arcseconds rises, and the models can reproduce both the amplitude and the radial variation of the observed dispersions and higher-order velocity moments without demanding extreme orbital anisotropies or unrealistic stellar mass-to-light ratios. Systematic exploration of parameter space shows that there is a relatively narrow range of central masses that yield good fits. Smaller central masses fail to raise the inner dispersion sufficiently, while larger ones overpredict the central dispersion and distort the shape of the velocity profile. The best-fitting models for NGC 3842 require a central mass of approximately 9.7 billion times the mass of the Sun, with uncertainties that reflect measurement errors, modeling assumptions and degeneracies among parameters, but that still place the mass firmly in the regime of the most massive black holes known in the nearby universe. The compactness of this inferred central mass is constrained by the spatial scales over which its dynamical effects are observed. The rise in velocity dispersion occurs within a region that is small compared with the core radius and the effective radius of the galaxy, implying that the additional mass is confined within a volume that is unresolved or only barely resolved by current imaging. If the same mass were distributed over a much larger radius, its contribution to the potential would increase the dispersion more gradually and over a larger region, producing a different radial profile than the one observed. This requirement of high central density rules out alternatives such as a cluster of ordinary stars or stellar remnants extending over large distances, because such a cluster would either have to be unphysically compact to remain bound without collapsing, or would produce observable light that is not seen. Models in which the central mass is provided by a dense cluster of dark stellar remnants, such as neutron stars and stellar mass black holes, are also strongly constrained by dynamical stability considerations and by the lack of any extended light component associated with such a cluster. Over long timescales, gravitational interactions among these remnants would cause the cluster to evolve, leading either to evaporation or to a collapse that would form a single dominant compact object. The timescales for such evolution, when compared with the age of the galaxy, favor scenarios in which the mass is already concentrated in a single massive object. Observations at wavelengths sensitive to compact sources such as radio and X-ray further constrain the nature of the central mass. In some galaxies with similar dynamical evidence for central masses, compact radio or X-ray sources, coincident with the optical nucleus, indicate low-level accretion onto a supermassive black hole. For NGC 3842, searches for such signatures yield at most weak emission, consistent with a central object in a very low accretion state, but not requiring high luminosity activity. The absence of bright nuclear emission is compatible with a massive black hole that is currently accreting at a low rate and producing only faint output, a situation often described as radiatively inefficient accretion. The lack of strong emission therefore does not argue against a black hole interpretation. Rather, it limits the current accretion rate and radiative efficiency. When the dynamically inferred mass is compared with empirical correlations between black hole mass and host galaxy properties such as the relation between black hole mass and stellar velocity dispersion, or between black hole mass and bulge luminosity, the central mass in NGC 3842 lies toward the high mass end and may exceed the value predicted by simple extrapolations of these relations from lower masses. This behavior is not unique to NGC 3842. Several brightest cluster galaxies host black holes whose masses appear large relative to these correlations, suggesting that the most massive systems may experience growth histories that differ from those of less massive galaxies, or that the scaling relations bend at the highest masses. In the context of NGC 3842, the large central mass aligns with its status as a very massive elliptical galaxy, at the center of a rich cluster, where repeated mergers and sustained accretion episodes at earlier cosmic times can build up both the stellar body and the central black hole. The conclusion that a compact central mass of approximately 9.7 billion solar masses resides in NGC 3842 therefore rests on a combination of factors: the inability of models without a central mass to reproduce the inner stellar kinematics within plausible ranges of stellar and dark matter parameters, the success of models that include such a mass in fitting the full set of kinematic data, the requirement that the mass be concentrated within a very small radius to match the spatial pattern of the dispersion, rise the dynamical implausibility of alternative extended mass configurations, and the consistency of the inferred mass with broader the scattered trends between central mass and host galaxy properties. Within the limits of current data and modeling techniques, these lines of evidence point toward the presence of a very massive compact central object, naturally interpreted as a supermassive black hole, embedded in the dense stellar core of NGC 3842. The compact central mass in NGC 3842 defines a gravitational sphere of influence, a region within which the potential of the central object dominates over the combined gravitational effects of the surrounding stars and dark matter. This sphere of influence is characterized in dynamical studies by a radius at which the enclosed stellar mass becomes comparable to the mass of the central object, or equivalently by the radius at which the contribution of the central mass to the circular velocity or velocity dispersion of stars is similar to that of the extended mass distribution. Inside this radius, stellar orbits are strongly affected by the central potential, and the kinematic signatures of the central mass become prominent in the observed line of sight velocity distributions. Outside this radius, the influence of the central object declines with distance and is gradually overtaken by the smooth potential of the galaxy and the larger-scale dark matter halo. For a central mass of approximately 9.7 billion times the mass of the Sun, and a characteristic velocity dispersion in the host galaxy of a few hundred kilometers per second, simple estimates place the radius of the gravitational sphere of influence at of order a few hundred parsecs, a scale that is large compared with the event horizon of the black hole but small compared with the effective radius of NGC 3842. In angular terms, at the distance of the Leo cluster, this corresponds to a region that can be partially resolved by high-resolution spectroscopic and imaging observations, allowing the dynamical impact of the central mass to be measured directly. Within the sphere of influence, the gravitational potential is dominated by the central mass, and stellar orbits respond accordingly. Stars move on bound trajectories that can be approximated to first order as orbits in a Keplerian potential, superimposed on a slowly varying background field from the more extended mass. The distribution of orbital shapes and orientations is set by the detailed history of scattering events, mergers and relaxation processes, and in practice is reconstructed through dynamical models that match the observed kinematic data. The line of sight velocity dispersion in this region tends to rise toward the center, reflecting the increasing speeds required for stars to remain bound in the deeper potential. This central rise is one of the key observational signatures used to identify and measure the central mass. The precise shape of the dispersion profile depends on the interplay between the gravitational influence of the central mass and the orbital anisotropy of the stars. In isotropic models where radial and tangential motions contribute equally, the dispersion increases approximately as the square root of the central mass divided by radius as one approaches the center, until limited by the resolution of the observations. In anisotropic models, the rise can be modified, but the requirement to reproduce both the central dispersion and the higher order moments of the velocity distribution constrains the range of allowed anisotropies. For NGC 3842, the observed kinematics within the central arc seconds show a clear enhancement in dispersion that aligns with the expectations for a massive central object and is not easily reproduced in its absence. The sphere of influence also affects the distribution of stellar orbits in phase space. Stars that venture close to the central mass can be scattered by its strong gravitational field, altering their energies and angular momenta. Over long timescales, this process can deplete the phase space region, occupied by low angular momentum orbits that pass near the center, an effect often referred to as loss cone depletion. The removal or redistribution of stars on such orbits is one mechanism proposed to explain the creation of shallow, central light profiles and cores in massive ellipticals. In this picture, the presence of a central massive object especially when part of a binary black hole at earlier stages leads to gravitational interactions that eject stars from the inner region, transferring energy and angular momentum to the binary and causing it to harden. The resulting stellar mass deficit in the core correlates with the mass of the central object. In NGC 3842, the size and depth of the observed core together with the large inferred central mass are consistent with models in which repeated interactions between the central mass or masses and stars within the sphere of influence have modified the central density profile over time. Dynamical relaxation times in the dense central regions of NGC 3842 are long compared with the age of the universe when computed for ordinary two-body encounters among stars, because the stellar density, while high, is not sufficient to drive rapid collisional relaxation in such a massive system. However, the presence of a massive central object changes the character of relaxation processes by enhancing the gravitational focusing of orbits that approach the center, and by providing a strong scattering agent that can redistribute stars more efficiently than star-star encounters alone. In addition, the earlier evolution of the central regions when binary black holes may have been present, following major mergers, involves collective dynamical effects that do not rely on classical relaxation and can act over shorter timescales. The current structure of the core and the stellar velocity field within the sphere of influence therefore encode not only the present gravitational dominance of the central mass, but also the integrated effects of past dynamical evolution in the central few hundred parsecs. The gravitational sphere of influence of the central mass in NGC 3842 extends beyond the region where the event horizon resides by many orders of magnitude in radius, so the stellar dynamics probe only the outer Newtonian regime of the black hole potential. In this regime, general relativistic corrections to the potential are small on the scales resolved by current observations, and the motion of stars can be modelled accurately using classical gravity. Nevertheless, the existence of a well-defined sphere of influence with a radius that matches the scale over which the velocity dispersion rises toward the centre, and over which dynamical models require a compact mass, provides strong evidence that the central object behaves as a point-like source of gravity, as expected for a supermassive black hole. The lack of any luminous extended central component that could represent a dense star cluster further supports this interpretation. Inside the sphere of influence, gas dynamics, where gas is present, also respond primarily to the central mass. In galaxies with significant central gas disks, the rotation curves of this gas can provide independent constraints on the central mass. For NGC 3842, the central regions are dominated by stars and hot gas with low densities, so stellar kinematics remain the main probe, but in principle any cold gas present on small scales would orbit under the same central potential. Future observations that resolve gas motions in the immediate vicinity of the nucleus could refine estimates of the sphere of influence and provide complementary checks on the mass derived from stellar dynamics. The concept of the gravitational sphere of influence thus provides a useful framework for interpreting the inner structure of NGC 3842. It defines the spatial scale on which the central mass governs the motions of stars and gas, sets the radius within which dynamical signatures of the central object are strongest, and links the observed rise in velocity dispersion and the presence of a core to the underlying mass distribution. In NGC 3842, the large mass of the central object implies a correspondingly large sphere of influence, making the dynamical effects of the central mass accessible to current observational techniques and allowing a robust measurement of its mass as part of a detailed dynamical model of the galaxy's central regions. The compact central object in NGC 3842 is described in general relativity as a black hole, an object whose gravity is so strong that there exists a boundary from which no signal, including light, can escape once it has crossed inward. This boundary is called the event horizon. In the simplest description for a non-rotating black hole with a given mass, the radius of the event horizon is directly proportional to that mass, so that more massive black holes have event horizons that extend to larger radii. In more realistic situations, astrophysical black holes are expected to rotate, and this rotation slightly modifies the detailed structure of the horizon and the region just outside it, but the overall scale of the horizon remains set mainly by the total mass. For a black hole with a mass of approximately 9.7 billion times the mass of the Sun, as inferred for the central object in NGC 3842, the characteristic size of the event horizon is of the order of a few hundred astronomical units. An astronomical unit is defined as the average distance between the Earth and the Sun, so an event horizon of this size would encompass a region several hundred times larger than the orbit of Earth. Expressed in terms of light travel time, the diameter of the event horizon corresponds to a duration of a few light days, meaning that light requires several days to cross from one side of the horizon to the other. This scale remains extremely small compared with the overall size of NGC 3842, or even with the radius of the gravitational sphere of influence, which extends to distances of a few hundred parsecs, but it is immense by the standards of stellar systems and planetary orbits. The event horizon of the central black hole in NGC 3842 can be contrasted with that of the central black hole in the Milky Way known as Sagittarius, a star. The mass of Sagittarius, a star, is estimated to be a few million times the mass of the Sun, so its event horizon has a radius of only a fraction of an astronomical unit comparable to the scale of the inner planetary orbits in the solar system. Because the radius of the event horizon scales linearly with mass, the event horizon of the NGC 3842 black hole is larger by several thousand times than that of Sagittarius A star. In angular terms, as seen from Earth, the Milky Way black hole subtends a much larger angle on the sky, because it is so much closer, and this has allowed very long baseline interferometry to resolve structures near its event horizon. The black hole in NGC 3842, although far larger in physical size, lies at a distance of hundreds of millions of light-years, so its event horizon appears far smaller on the sky and remains beyond the reach of current direct imaging techniques. Its presence is therefore inferred indirectly through its gravitational influence on nearby stars and gas, rather than through direct observation of the region around the horizon. The event horizon defines the region from which no information can escape to distant observers, but the gravitational influence of the black hole extends smoothly outward beyond this boundary. Just outside the event horizon lies a region where stable circular orbits for test particles exist only down to a certain radius, often called the innermost stable circular orbit. For a non-rotating black hole, this orbit lies at a radius equal to 3 times the event horizon radius, while for a rotating black hole the innermost stable orbit can be closer in for prograde orbits or farther out for retrograde orbits. In an accretion flow, gas spirals inward, and in the simplest models releases gravitational energy as radiation down to this innermost orbit before plunging across the horizon. For a black hole as massive as that in NGC 3842, the innermost stable orbit still lies at a radius of the order of hundreds of astronomical units, which is large in absolute terms, but represents a very small fraction of the size of the host galaxy. If gas reaches these radii, the orbital periods are of the order of months to years, much shorter than typical dynamical timescales on galactic scales, but long compared with the light crossing time of the horizon itself. The gravitational potential near the event horizon is extremely deep, and any infalling matter accelerates to speeds close to the speed of light as it approaches the boundary. In general relativity, the curvature of space-time in this region is strong, leading to phenomena such as gravitational redshift, in which radiation emitted from near the horizon is shifted to longer wavelengths as it climbs out of the potential well, and gravitational lensing, in which light paths are strongly bent. In the context of NGC 3842, these effects shape the behavior of any radiation originating from the innermost regions of an accretion flow, though at present such radiation is weak or absent at observable wavelengths, consistent with a low accretion rate. On scales larger than the event horizon and the innermost stable orbit but still within the gravitational sphere of influence, gas motions and stellar orbits respond primarily to the central mass in a regime where Newtonian gravity remains a good approximation. Here, the potential of the black hole adds a steep central component to the overall gravitational field, and orbits can be approximately Keplerian over a range of radii, with orbital velocities set by the balance between gravity and centrifugal forces. The transition from this regime to the domain where the extended mass distribution of the galaxy dominates occurs near the radius of the sphere of influence. For NGC 3842, the large mass of the central black hole implies a correspondingly large sphere of influence, so the region within which stellar motions are directly sensitive to the black hole extends to distances that can be probed by current optical and near-infrared observations. This situation contrasts with lower mass galaxies where the sphere of influence can be so small that it is only marginally resolved. The comparison between the NGC 3842 black hole and Sagittarius A star illustrates how central black holes in galaxies span a wide range of masses and corresponding horizon scales, yet follow broadly similar physical principles. In both cases, the event horizon defines the boundary of no return, and the gravitational field outside the horizon is described by solutions of the Einstein equations determined by mass and spin. For smaller black holes, such as those in stellar mass X-ray binaries, the event horizon radius is measured in tens of kilometers, and the innermost orbits lie on scales comparable to the size of a compact star. For supermassive black holes in galactic nuclei, the same equations apply, but the characteristic lengths and timescales are stretched by many orders of magnitude. In NGC 3842, this scaling produces a black hole whose event horizon is comparable in size to the orbit of the outer planets in the solar system, while in effect remaining a point-like source of gravity when viewed from the perspective of the host galaxy. The fact that the event horizon radius increases in proportion to the mass, while the sphere of influence radius scales roughly with the ratio of central mass to the square of the velocity dispersion, means that for very massive black holes in galaxies with high dispersions, the sphere of influence can grow enough to be resolved even when the horizon itself cannot. This relationship underpins the dynamical measurements of the central mass in NGC 3842 and in other massive galaxies. Thus, while the event horizon remains a theoretical boundary inferred from general relativity, rather than a directly imaged surface, in this case its predicted size and the associated gravitational effects provide a coherent framework for connecting the compact central mass measured from stellar dynamics with the broader physical description of a supermassive black hole at the center of NGC 3842. In its present state, the central black hole in NGC 3842 appears to be accreting material only weakly, if at all, when compared with the luminous active nuclei and quasars observed at earlier cosmic epochs. Observations across multiple wavelengths place strong limits on any current high-energy emission from the nucleus. Optical spectra of the central regions lack the strong broad emission lines that characterize classical unobscured active galactic nuclei, and narrow line signatures, if present, are weak. X-ray observations do not reveal a bright, compact nuclear source with luminosity comparable to that of actively accreting quasars at similar black hole masses, and radio data show at most modest nuclear radio emission. These indicators are consistent with a nucleus in a low luminosity state, in which the accretion rate onto the black hole is far below the maximum sustainable rate, set by the balance between radiation pressure and gravity, often called the Eddington limit. In such a regime, accretion flows are expected to be radiatively inefficient, with much of the gravitational energy of infalling gas carried away by mechanical outflows, or advected into the black hole rather than converted into radiation. For a black hole with a mass of approximately 9.7 billion times the mass of the Sun, an accretion rate near this limit would produce an enormously luminous quasar, but the absence of strong nuclear emission in NGC 3842 shows that the present accretion rate is many orders of magnitude lower than this hypothetical maximum. The available fuel for accretion in the core of the Leo cluster is dominated by the hot low-density gas of the intracluster medium and the galactic corona around NGC 3842. Gas at these high temperatures is only weakly bound on small scales, and can flow toward the center at rates set by processes such as radiative cooling and the pressure structure of the atmosphere. Simple estimates of spherical accretion from hot gas, sometimes called Bondi accretion, indicate that for typical densities and temperatures in cluster cores, the mass inflow rate onto a central black hole can be sufficient to power low luminosity, active galactic nuclei, even when the radiative efficiency is small. In NGC 3842, if gas is accreting in this fashion, the resulting luminosity appears to be modest, suggesting that the combination of accretion rate and radiative efficiency yields only weak emission that is difficult to detect against the bright stellar background of the galaxy and the diffuse X-ray glow of the surrounding gas. This situation resembles that in many nearby massive ellipticals and brightest cluster galaxies where central black holes are identified dynamically, but nuclear activity is faint or intermittent. The current quiet state of the NGC 3842 nucleus does not, however, reflect the full growth history of its black hole. To reach a mass of nearly 10 billion solar masses within the age of the universe, the black hole must have experienced phases of significantly higher accretion in the past. This inference arises from models of black hole growth that integrate plausible accretion histories, and from the observed population of quasars at higher redshifts, whose integrated light and demographic properties can account for the present-day mass density of supermassive black holes if typical growth proceeds through luminous accretion episodes. In these models, the most massive black holes spend part of their history accreting at rates not far below the Eddington limit, producing quasar luminosities that would outshine their host galaxies and generate strong ionizing radiation and energetic outflows. For NGC 3842, no direct record of such a quasar phase is visible today, because any luminous episodes would have occurred billions of years ago, and the associated radiation has long since propagated away. However, indirect signatures of past activity can persist in the structure and thermodynamic state of the surrounding gas. In many cluster cores, X-ray observations reveal cavities in the intracluster medium regions of reduced X-ray surface brightness that align with radio lobes and are interpreted as bubbles inflated by jets from active galactic nuclei. These bubbles rise buoyantly through the hot gas and deposit mechanical energy that can offset radiative cooling. The energy required to inflate such cavities is comparable to the energy expected from accretion onto central black holes at modest fractions of the Eddington rate over tens of millions of years. Where similar structures are observed in the Leo cluster core, they indicate that the black hole in NGC 3842 or its immediate predecessors in earlier stages of the galaxy's assembly, has injected energy into the surrounding gas through jet activity. Even if current radio and X-ray signatures of such jets are weak, the cumulative effect of past outbursts can influence the temperature and entropy profiles of the intracluster medium and contribute to maintaining the low cooling rates inferred from gas observations. The chemical enrichment of the gas in the cluster core also reflects in part the integrated impact of active galactic nucleus feedback, because outflows can redistribute metal-enriched gas from the galaxy into the intracluster medium. The large mass of the black hole in NGC 3842 and the presence of a massive metal-rich stellar population in the host galaxy suggest a long period of coevolution in which gas inflows at early times fueled both star formation and black hole growth, followed by a more quiescent era in which the supply of cold gas diminished and feedback from the central engine helped to prevent catastrophic cooling of the hot atmosphere. During the growth phase, mergers with gas-rich galaxies as well as the collapse of dense gas clouds within the protocluster environment could have delivered substantial amounts of cold gas to the central regions, driving high accretion rates and episodes of luminous nuclear activity. As the cluster assembled and the intracluster medium was heated to high temperatures, the availability of cold gas decreased, and the typical mode of accretion shifted toward the low-rate hot gas-dominated regime seen today. In this later phase, the black hole continues to gain mass but at a much slower rate, while its feedback operates primarily through mechanical rather than radiative channels. The current state of NGC 3842, with an old massive stellar population, a hot surrounding atmosphere, and a dynamically measured central black hole of nearly 10 billion solar masses fits within this general framework. Its black hole mass lies at the high end of the distribution for nearby galaxies and appears large relative to some empirical correlations between black hole mass and host galaxy properties, a feature shared with other brightest cluster galaxies. This suggests that in the densest environments, the coupling between galaxy growth and black hole growth can differ from that in lower mass systems, perhaps because merger-driven gas inflows and cluster-scale processes play a more prominent role. The present dynamical and thermodynamic properties of the NGC 3842 system, including the structure of its core, the velocity field of its central stars, the state of its hot gas, and the scale of its gravitational sphere of influence, are consistent with the scenario in which an exceptionally massive black hole, assembled through a combination of early rapid accretion and later low-level growth, and now resides in a low accretion, low luminosity state. In the nearby universe, this black hole exerts its main influence through its gravitational field, which organizes the motions of stars in the inner galaxy, and through intermittent or weak feedback that helps regulate the surrounding hot gas while its past luminous phases are recorded indirectly in the mass it has accumulated and in the long-term properties of the galaxy and cluster core that it inhabits.